Okay, have a quick think about this to start with. So, who produces the bigger force? Because mechanics so far, this chapter you've seen, it's all about forces, right? A man weighing 80 kilos, accelerating at 4 meters per second, or a man almost twice the mass, 150 kilos, accelerating at 2 meters per second squared. So the answer is the first one. Why is it the first one? Well, you've probably got some intuitive idea already that, like, if things are moving and they're moving quickly, that they give off more force, which is kind of correct. But really, what you're picking up on there is the acceleration. So when somebody accelerates, if they like move their body really, really quickly when they're implementing a force, that's the acceleration element. Okay. So mass is important, but it's not everything. Just having a high mass will not guarantee that something has a large force, for example. So there's more going on than just looking at mass. In other words, we really need to think about masses and acceleration. And in fact, those two things come together to give us force. So Newton's second law of motion, and an equation you are going to use hundreds and hundreds of times, okay, is F equals ma. Now, what does the F mean? It is not force. It is resultant force. Resultant force. In other words, overall force. Resultant force equals mass times acceleration. Do not say, please, 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 do not say it's force equals mass times acceleration, because that will put you down the wrong path. I guarantee that will cause you to lose marks, okay? Resultant force equals mass times acceleration is how you need to say this and how you need to think about it. So if you haven't already, make a note of this now, please. It will save you a lot of pain and lost marks in the future. Resultant force equals mass times acceleration. So, you've got a couple of images here to sort of demonstrate the point that if you have a small force, you have a small acceleration. And if you have, a much bigger mass, think about a person versus a penguin. The force is much, much greater. Okay. Here's another example. So, small children, you're talking about small masses, and the acceleration there as you walk is very, very, very slow. Okay. So there is a force there, but the force is very slow. Okay, this example here, the football player has a much, much, much bigger mass and is really deliberately accelerating with their arms, which creates an awful lot of force. So high masses, high accelerations will lead to high resultant forces. Okay, let's do an example of putting this into practice. So this is the first time really that we're getting to sort of a more mechanicsy question, bring it all together now. A car of 2,000 kilograms, well, that is a mass, isn't it? It has a driving force like it's pulling it forward, okay, of 800 newtons. That's a force. And forces of 200 newtons, again, newtons, this is also a force, resisting its motion. Determine its acceleration. So we're going to do these steps here. We've got masses in the question, we've got forces, and we're being asked about acceleration. So you can see here that we might want to use this one. So first step, the diagram. Draw like a plane. A plane could be sort of like the road, and it's a box. Really, it's a particle. So you could draw it like that. You might sort of draw it like that. It's the same thing, okay? Now, straight down, well, this is a force diagram. There is a force acting down. So what force pulls the car down? Why can't the car just float around? Well, it's weight. This is not a mistake here. This is the mass times by gravity. This is a force diagram. It's not a mass diagram, it's a force diagram. So the downwards force is its weight, which is given by mass times gravity. So in other words, with forces diagrams, for vertical arrows, you will see G written an awful lot. Keep it written as G instead of 9.8. It makes things easier and tends to cancel out later on. Well, hang on a second. Why is the car not sinking into the ground? Why is it not accelerating towards the center of the earth? Well, that is because there's something acting against. Well, it's a plane, so it's sort of a surface. A surface has a reaction, a normal reaction. Now, this is a little bit confusing because they're using R, but this is actually a reaction, a normal reaction. Stops the things sinking into the plane, okay, which is a road in this example. What else? Well, if you're right-handed, or I guess maybe even left-handed, you probably have a bias for putting driving forces acting towards the right-hand side. I know I do. So I would draw my 800 going to the right. It doesn't have G on it because it's not a weight. It's just a force. It's already a force, 800 newtons. And 200 newtons resisting. Well, if it's resisting, it's working against it. So that must be going the other way, 200. Okay, so we've drawn our force diagram. Now, we want to talk about the acceleration of this car. So, am I talking about its horizontal acceleration or its vertical acceleration? Just think about that for a second. It might sound like a stupid question, but if you have forces involved and people are saying, what's the acceleration? They could be talking about either. Well, here they're talking about horizontal. Okay, it sounds obvious, but they're talking about the horizontal acceleration. So, we need to consider the horizontal resultant force, because F equals ma means the resultant force equals mass times acceleration. We've got, or we can get, we haven't got it yet, we can get the resultant force. We have the mass of the object. The m means the mass of the object, which is a car here. And a is what we're trying to find. So the resultant force in the horizontal direction, let me see if we have something that's going to come up. The resultant force in the horizontal direction is going to be 600. Okay, so 800 minus 200, 600. Is equal to mass times acceleration. Mass has to be in kilograms, okay? So 2000 times A. And you can see we end up with our answer there. Seems really, really, really straightforward. So I would encourage you not to just like neglect the ideas there, that you need to think about all of the forces. Mass is not weight. What F really means, okay? Because for the harder questions, this is where you will drop marks. So get into good habits really, really early on. Okay, weight equals mg. Well, we saw that already. It's just there for you to make a note of as a reminder. So have a go now at the your turn here. Okay, on the right hand side, pause the video, have a go at that question. So I'm going to assume that you've had a go. Your force diagram should look something like this. It shouldn't be 70, but 70g, because it's a force diagram. It's not a mass diagram, it's a force diagram, and weight is a force. 300 is the resistance, in other words, it's acting against it. What's its acceleration towards the ground? Well, it would seem sensible here to make downwards the positive direction, okay? Because you probably have the idea 70g is the bigger force and it's held back by 300. Okay, so 70g is the driving force minus what's holding it back. Well, this is your resultant force, isn't it? That's your F, your resultant force. 70, that's the mass of the sheep. Okay, and we get our answer here. Why does it sound sensible? Well, it's falling towards, so we expected a positive answer for acceleration. Why is it not 9.8? You might say, I thought gravity is 9.8. Why is it not 9.8? Well, it's being held back by some resistance, okay? It's not in free fall, it's being held back. So we need to use F equals ma. Okay, let's just have one more quick look. How many questions have we got here? So we'll do one more example fairly quickly, and then it will be your turn. So we'll just leave that line there. Since F equals ma involves force and acceleration, yes, it allows us to connect calculations involving forces with SUVATs, yes. So this is an interesting point now. If we can work out acceleration, well, acceleration is one of those values, isn't it? It's that one there. So if we were given some information and then we worked out A, well, maybe they might ask us to find out a fourth piece of information. If this sounds unfamiliar to you, please watch the videos on the chapter before. So a body of mass 5 kilograms is pulled along a rough horizontal table. Well, there's the table. Rough horizontal table. I'm expecting some force holding it back. Mass of 5 kilograms is pulled along by a horizontal force of 20 newtons. I might not always do this, but you should always be doing this, okay? Underlining the information, making sure you're using it all. Well, can we draw some of that? Yes, we can. The block has a weight. it must have a reaction as well if it's on a table, because otherwise it would be going through the table. It's being pulled by 20 newtons. That could have an n on the end or 20. It's sort of up to you. Against a constant friction force. So a friction force of 4 newtons. Well, what's friction going to do? Does it want to help the thing move even faster, or is it trying to hold it back? It's trying to hold it back. Okay, so that's why there's a 4 there. Find the acceleration of the body. Are they talking about acceleration like into the sky or down to the ground? No, because it's on a table. They're talking about the horizontal acceleration. So we want resultant force equals ma, and this is going to be for the horizontal direction. Okay, so what's the resultant force? Well, it's 16. It's 20 minus 4. The mass, yeah, there it is, 5, and the acceleration, that's what we're trying to find. So acceleration, it makes sense here, positive directions to the right, will give you 3.2. Okay, now, what's the distance traveled by the particle in the first 4 seconds? So you just found acceleration. T has been given in the question. Let's see where this u equals 0 came from. Initially at rest. So that's something that I didn't underline, that we should have underlined. If you don't underline that, you can see that that will cause problems. So 1, 2, 3, the distance, that's s. I can link them together. Okay, so things about forces turn into SUVAC questions because acceleration's involved. And if the acceleration is constant, and the acceleration will be constant if the forces are constant. Okay, if the acceleration is constant, you have SUVAC equations. The magnitude of the normal reaction between the body and the table. Well, we probably need to go back for that one. The magnitude of the normal reaction, that's that one there, isn't it? Between the body and table. What's that one there? What is R going to be in this situation? Are you expecting it to float away or sink into the table? Hopefully your answer is no. It was 5g down. The only other force, 5g and R, these were the only vertical forces. So if it's in equilibrium, which is what you assumed, okay, you assumed that it was in equilibrium, and that's a fair assumption, they need to be equal to each other. And 5g is also the same as 49 newtons. Okay, that would be, like maybe like 1 mark or something like that. I'd like you now then to pause the video and have a go. Lots of information there, so you're going to really need to read through that quite carefully. Okay, but I'd like you to slowly have a go and try and pick it apart. And you're seeing the wordiness here is coming from combining chapters 9 and 10 together, which will start to happen. Okay, so let's take a look at this now. It's going to be a tricky one because this is part C. So A and B is being removed. There's probably some redundant information in here that's not important. Let's take a quick look. So what are we trying to do? You have to give me a second. I haven't done this question recently. The point A, the ground is soft. After P reaches the ground, it sinks vertically downwards into the ground before coming to rest. Coming to rest sounds like a V equals 0. Mass is 4, okay. The ground is assumed to exert a constant resistive force of 5,000. Okay, so it seems to me we've got some particle going sort of is in the ground and sinking into the ground, sinks vertically downwards into the ground. Okay, it's going to have a weight. Okay, this is going to have a weight to it. It's also going to have a resistance. So resistance is going to act the opposite way. So I've got this one here before coming to rest. So I'm trying to separate the parts here because I feel like I've got an F equals ma, and then I've got a SUVAC all put together. So we've got 5,000 here, and what's causing it to go down? The thing that's causing it to go down is its weight, isn't it? So this here should be 4g. So 4g minus 5,000 is the resultant force, unless there's anything else going on. And that will be equal to its mass, which is 5, times its acceleration. Okay. So it should have some sort of acceleration here. Let's take a look. So 4g minus 5,000 equals 4a. Oh, sorry, that's my mistake. It's 4 kilograms. Now, you're going to get a number here that I would expect to be a negative number. Why is it negative? Well, I've taken downwards to be my positive direction, and it's sinking into mud. So you threw the thing, it's traveling, it's traveling, it's traveling. Well, when it gets into the mud, it's going to slow right down. So it's going to decelerate. It's going to be a negative number. So you're going to get your acceleration value, and then we're going to try and use other bits and pieces. So if I write my suvat out, I will know my acceleration. I saw, where did I see it? Coming to rest, v equals 0. I've got that one there. The vertical distance, that's the one that I want to find. So I need u or t. Well, the bit above was about the speed of the particle. The particle p moves freely under gravity until it reaches the ground with speed 28. I think that's my number there. So that's my 0, my 28. I haven't worked this one out yet, but we can work that one out. There we go. Okay. So v squared, so u squared to a. Look at that. That number there, a, is a negative. It's a big negative, but that's because the thing had 28 meters per second, and then it's like stopping. It's sinking into the mud. It's going to slow down really quickly. Acceleration, and s that I don't know. Sorry, v we knew as well. So look at that. We can actually find our answer for that. Okay, quite a tricky problem there, but if you read the information slowly and you really think about it, it can be done. Okay, so that takes us to 10C for forces.